Yeah, the title of the paper is essentially talking about implementation of true time delay in a digital application, in an RFSoC application. So I'll just give a little introduction to Slipstream because people might not know who we are. Talk a little bit about the motivation behind why we're doing this work. I've got a little bit of MATLAB code just to show how beamforming works. Talk a little bit about true time delay and implementation of that in the digital domain rather than the analog domain, and talk about how we've done that on the implemented that on the RFSoC device, which I'll explain what that is later on, and just a couple of little results. So yeah, with Slipstream Design, we're predominantly a bunch of RF and digital designers, and we operate really from the samples all the way to the antenna. We're based up in Shipley, where all the best companies are, Alex. And there's 21 of us in total, and we're pretty much 50-50 split between digital and RF. This just shows a picture of some of the types of work that we do. So we get involved in the nitty-gritty of RF design. In the middle of there's an 800-watt CWPA that we did last year. But over on the top right is a little bit more linked to this presentation. That's a custom implementation of a RFSoC. RFSoC means RF system on a chip, which is actually a Xilinx device. And then there's a few other examples of the type of work that we do there. So yeah, the motivation behind this type of work is that we're aiming to develop a flexible radio platform for use in various applications. Ideally, we want it to be application agnostic, really, and we're leveraging the use of software-defined radios wherever possible. Because modern high-speed data converters, which are readily available these days, can relatively easily generate signals up to 6 gigahertz. So trying to leverage that technology as much as possible. And we're aiming to address hardware bottlenecks and investigate wideband techniques. So working towards fully reconfigurable radio systems is the main sort of ethos behind this type of work. So maybe a few years ago, a typical transmit-receive radio chain might look a little bit like this, where you've got two stages of up and down conversion. Predominantly, that's because of the lower frequency of the DACs and ADCs. So the local oscillator has to be reasonably close to the RF frequency. So to get that selectivity, you often had to have multiple stages of up and down conversion. And today, a lot of the work that I do, I quite often see now in systems, in various systems in radar and comms, we have this sort of single stage of down conversion, and a lot more of the radio chain. So that second stage of down conversion is moved into the digital domain. So you'd often see digital down conversion to take the signal down to baseband. And the IF frequency where we interface with the DACs and ADCs is now typically a few gigahertz. So you see, quite often see IF frequencies of, 1.5 gig, and sometimes in some applications we've worked on, the IF frequency, up as high as 3 or 4 gig. The higher you can get it in some ways, the better, because that spaces the local oscillator and RF signal apart, and that eases the RF filtering. But maintaining this single stage of down conversion, up and down conversion, allows you to sort of maintain the selectivity that you get from having the IF filters, those narrowband IF filters. This is quite a common topology that we see. That's pretty much what I just said. So yeah, a key aspect of our aim to make this flexible radio platform is to leverage the digital hardware wherever we can, and to increase the flexibility in the RF hardware. So we kind of got these two chains, got the digital side, and then we also, although I'm not going to talk about it here, we're also working on a sort of flexible power amplifier technology as well. But today we're talking about the digital side of things. But there's an RF slant to it, because we're talking about things that would previously have been done in the RF domain now being moved into the digital domain. So I got MATLAB out and decided just to put together a few little plots just to help describe what beamforming is. So this is just a single isotropic emitter, so radiating in all directions, like a ripples on a pond. And there's, the signal's going in all directions. But if we just add another emitter, we can immediately see we're starting to get some cancellation out to the sides and some addition. And we're starting to see a beam forming, even just with the two antennas. And if we increase that up to four antennas, you see, if you use your imagination, you can see a beam propagating in both directions. Normally, in a system, you'd only have the forward-going wave, but this just shows the fundamentals. This is a fixed beam going off in one direction. And as I think we all probably know, if we adjust the phase to each of those elements, we can steer the beam around. And this is just a two-dimensional cross-section through a 16-element array, which just shows how the beam can be steered around by adjusting the phase shift to each of the elements. So this all assumes a fixed frequency. But ultimately, it's the phase of each element that needs to be adjusted to form the beam, and the required phase shift is governed by this equation here. And the key thing to take away from this really is that the element phase shift increases. The required phase shift increases as we change the frequency. So if we don't compensate for that, then we can have problems such as beam squint, which I'll talk about in a moment. So this just drives that home really. So what we've got here is an array designed for 1 gigahertz, and at 1 gigahertz on the first element we have a 0 degree phase shift. The second element wants a 90 degree, and then 180, 270 for the other elements. But we're just concentrating on the frequency and the second element there. As you can see, as we increase the frequency, then we can see that the required phase shift to maintain a 30 degree steering angle in this case increases. So it's going up from 90, 99, 108. And that can be achieved by just using a simple transmission line. So here we've got a transmission line at the bottom, which is 75 millimeters long. And at 1 gig, that gives us 90 degrees. And just because it gets electrically longer as we increase the frequency, then we get increased phase shift. And that gives us exactly what we need. So a time delay gives us the perfect, maintains the beam angle, even if we change the frequency. The problem with time delays is that they're difficult to implement. It's not easy to have an array of, say, for example, switched transmission lines. That is one way to do it. A much easier way to achieve, a variable phase shift is to use a phase shifter, obviously. But phase shifters have, as you can see in this plot in the top right here, the time delay. That's a visual representation of what I've just talked about. The phase shift between the two elements as you increase in frequency diverges. But with a phase shifter, the relative phase between the two states remains constant with frequency. So if we're using narrowband signals, it's totally fine to update the phase shift when we change frequency of operation. That's no problem. But the problem comes if we use signals with sort of wide instantaneous bandwidth, such as like an OFDM signal, which contains many frequencies. Maybe could have a instantaneous bandwidth of hundreds of megahertz. So it's not possible to update the required phase shift at that kind of rate. So time delay is what we would like. Oh, just a little bit here. This is just driving that message home. An example, one way to make a phase shifter is to use hybrid coupler with a couple of varactors on, and then the signal is reflected off those varactors and then recombined at the output. And there's a plot here on the bottom right shows the blue lines shows two different phase states, and we can see for this configuration we can see that constant phase shift between the two phase states. And I've overlaid there on the red trace, you can see two transmission lines giving us this increasing phase shift between the two states, which is what we're after. Okay, so if we use a phase shifter as opposed to a time delay elements, then we have this problem where the sort of coherent addition of the signals doesn't always happen. It moves around because as we sweep frequency, the point of addition physically moves in space, and this is called beam squint. And these animations here just show what happens with if we use phase shifters and then we sweep the frequency. In this case, we're sweeping from 1 to 1.5 gigahertz, and you can see at 45-degree beam angle, we're getting a beam squint of 16 degrees there. We're also starting to get some grating lobes coming in, because as we increase the frequency, the array size is staying physically the same. And so effectively, the electrical size of the array is changing. So the spacing between the elements is changing. So I see this other beam starting to come in the top left. But the main point here is that the beam, as we sweep frequency, the beam is changing its direction, which is typically a non-ideal scenario. And just as a point of interest, the amount of beam squint depends on the pointing angle. So at the bottom right there, we have a 5-degree beam angle. We can see that the squint is still there, but it's much less. So this is, if we were to steer the beam using delay elements, this is what it would look like for a fixed beam angle. So we've got a time delay, and then for the second element we have 2 time delays, the third element 3 time delays, and this points the beam off to the right. So this is kind of what we're trying to achieve. So if we do, what I've done here is just updated the simulation to steer the beam using time delays, and it's the same exactly like we had a moment ago. And now you can see, instead of the beam, as we sweep from 1 to 1.5 gigahertz, we can see that the beam angle is remaining constant. The side, we get the grating lobe, as I talked about again, and also the width of the beam is breathing in and out because of the array changing size. But the key is we've got rid of the squint. What we're trying to do here. So the challenge is to have an adjustable time delay on each element. As I spoke about earlier, that's not the easiest thing to do in the analog domain. So the requirements for what we need for a typical time delay based system are given on this slide. So we've assumed a 1-degree pointing accuracy and a 60-degree required beam steering angle. So to achieve that, we need to be able to adjust the delay from 4.5 picoseconds up to 3 nanoseconds or 3,000 picoseconds. So that 4.5 picoseconds is a small amount of time. And just to put that into comparison, we said one way in the digital domain, one way to achieve that is just by shifting the signal by a clock cycle. But the devices that we're using, and typical really, these are reasonably fast, but we've got 9 gigasample DAC clock rate. Even then, we've still only got 101 picoseconds between clock samples. So integer delay only gives us 101 picoseconds, but we're after 4.5 picoseconds of delay. So we need fractional delay in order to get what we need here. So another approach is to leverage the time delay properties of filters. And an ideal low-pass filter has a constant group delay characteristic. So in the bottom right is the group delay characteristic of an ideal low-pass filter. And we in the RF world, we tend to think of filters in the frequency domain, but in this case, we have to kind of think of it a little bit more in the time domain. So the impulse response in this case of that filter is a sync function in the time domain, as is shown in the bottom left here. So yeah, we need to think about it in the time domain. So a fractional delay, as I've said, really means achieving a delay finer than a single clock cycle, and we achieve this using finite impulse response filters. And as we see, the equation here is really just the equation of a sync function, and that sync function is what we need to effectively program into the taps of the FIR filter. And when we're off integer values, then we have to apply a weighting function as well, but that's kind of a detail really. So as I said, the coefficients of the FIR filter is the sync function. So so for every beam angle, we need a set of coefficients. So if we want to change the beam angle, we have to update the coefficients. So I have an example here of an integer delay. So on the left, we have a it's effectively a pulse going into our filter, and we're set here for integer delay, and we just move that sync function from one sample to the next, and we can achieve this level of integer delay. But what we've got on this plot is just showing what we can do is with the impulse response in the digital domain, we can slide the impulse response along in time arbitrarily. And as we slide the impulse response along in time, then we can achieve, this is just zoomed in on the right here on the leading edge of the output, we can achieve a fractional delay, almost an arbitrary level of fractional delay on that leading edge of the pulse. So there we've sort of achieved our aim of implementation of fractional delay. So yeah, the summary of the fractional delay part is that by using the digital processing techniques, it's possible to implement that using FIR filters, and each beam angle, crucially, has its own set of FIR coefficients, finite impulse response coefficients. It has a finite bandwidth due to the truncation of the FIR filter in a discrete system, but we can typically achieve up to sort of 0.3 of the sample rate. And the bandwidth can be achieved by increasing the number of taps, but then there's a trade-off there between the storage requirements, because there's a lot of coefficients to store for all these beam angles, and the rate at which you can update the beam angle. But the bottom line is that you can adjust the group delay of that filter to arbitrarily to give you fractional time delay in the digital domain. So this approach, talking about how we've implemented this approach can be implemented on any FPGA or DAC ADC combination. But since we're interested in a compact form factor and also multiple channels, we've chosen the Xilinx RFSoC, RF system on a chip, which is a full multi-channel radio on a chip. So it's 40 by 40 package, and there's quite a lot going on inside the package. There's a Zinc FPGA in there, eight DACs, 8 ADCs all running. The DACs running, let's say, about 9 gigahertz. The ADC is about 6 gigahertz. And then we can directly generate signals out an analog bandwidth of about 6 gigahertz. It's got a number of ARM Cortex processors. And then the other side of it, we can connect directly to GTY transceivers, to like an optical transceiver. So you kind of got optics one side and then RF the other, all in this sort of 40 by 40 package. So as I say, there's quite a bit going on. And part of the advantage is you can, 1 minute it can behave like a beamformer, and then you can almost completely reconfigure the firmware to make it behave in a different way, which is part of the attraction for this sort of flexible radio platform. So although we're developing our own RFSoC board, which is up in the top right, which we call Astro's little FMC-based RFSoC board, the experimentation work that we did here was on a Xilinx ZC111 Gen 1 RFSoC board. There's a picture of it there, and there's a picture in the lab of a couple of boards. Part of the challenge with these types of things is making them work together, so synchronizing multiple devices to work in synchrony, whilst maintaining coherence between all the outputs. So that's why we've got two boards there. I've not got a huge amount of data, but there's some pictures. I've got a couple of pictures here. So we developed an application just to generate two outputs. So we've got two DAC outputs from the RFSoC, 1 gigahertz tones, and here the green trace is leading the yellow by 60 picoseconds. And then by putting the signal through the FIR filter, we can then add a delay of 160 picoseconds in this instance. We can go a lot lower if we want. This is the one that I could show you, and now we lag by 100 picoseconds. So this is just showing that we're able to sort of control the phase of the two outputs. Just a couple of slides. So for very small phase differences, we would use a VNA for the measurement. So we would directly use the receivers on the ZMB 40 that we've got. So we remove the external jumpers and go straight in and do that. Allows for much more precise phase measurements between the two input signals. because although we've got high-speed scopes, we need extremely high-speed scopes to see some of these small time delay differences that we're talking about. That's just a little bit on how we do some of the measurements. So in summary, we've made I would say, our first steps towards sort of implementation of digital beamforming based on true time delay, which helps lead towards this wideband array idea. And as part of the flexible radio platform, we've demonstrated that on a RFSoC device. And then future steps are to implement that with real antennas and do some actual through-the-air beamforming to demonstrate this with wide instantaneous bandwidth signals. So thank you very much for your attention and for hanging on.
Thank you very much, Mike. Does anyone have any questions? Alex?
Don't worry, Mike. It won't be
difficult. I'm sure it will be.
So that's a nice technique. That's nice. When we compare the unshifted and the shifted plot, I see there was obviously a change in magnitude on the shifted. What does the magnitude response of the FIR filter look like as you introduce delay? Do you introduce ripple?
You do on the fractional delays, yeah. So for the integer delays, because all of the taps away from the delta function, you know, the one in the middle, the delta function, all of the taps are 0 out to infinity. So they can be truncated without causing any ripple. But as soon as you move off from the integer delay to the fractional delay, all of those taps, ideally, they have a real value out to infinity. And when you truncate it, that causes ripple in the time domain. And so that's why we have to apply a windowing function there to help minimize the ripple.
Okay, thanks.
Anyone else?
Thank you. So how many taps are you using in this sync filter, and are you concerned of the extra complexity that you have in the phase shifting? So instead of having a single complex multiplication, you will have an FIR multiplication now.
I don't know exactly how many taps we're using in the FIR filter. So that's not I've not actually implemented it myself, so I'm not completely sure, but I can get back to you on that.
Thank you.